Section 10.2, Law of Cosines. This is going to give us our second major tool for working with oblique triangles. In the last section, we were working with law of sines quite a bit, and we saw that that is really helpful. There are plenty of applications and areas where that can help us solve for missing sides and angles in oblique triangles. But it turns out that there are certain limitations of law of sines. So one is if we have all three side lengths, like let's say we're looking at a triangle like this one over here, ABC, and what if we know the side lengths A, B, and C? We have all those, but we're trying to solve the triangle. We're looking for those three angles, right? Alpha, beta, and gamma. Well, how would we, attempt to use law of sines to find those angles? Well, we would set up some kind of proportion like this, like maybe sine of alpha over A is equal to, how about set that equal to sine of beta over B, right? And we would have values to substitute in for A and B, right? But we wouldn't have either alpha or beta to substitute in. So we're going to be stuck with more than one variable in this one equation. Okay, and if we have two variables in one equation, it isn't going to be defined for a single value. We won't be able to solve for either of those angles. Okay, so law of sines simply falls short when we're trying to solve for angles given three sides. We run into a similar problem if, let's say, we have two sides and the angle in between those two sides. So let's say, instead of those side lengths A, B, and C, what if we had side length A, side length C, but we knew this angle beta and we wanted to solve this triangle? What would happen here? Something similar, right? Like maybe we would set up this. What if we said like, okay, sine of beta over B, just using sine of beta naturally because that's the one angle that I have. And then how about I use sine of alpha over A, right? I have A. So I would have this value and I would have this value, but I don't have alpha, right? I don't have either of these other two angles, alpha or gamma. So again, we're stuck with one equation and two unknowns. So we simply are not able to solve this triangle with law of sines alone. Okay, one other issue that happens is supplementary angles. So the sum of all these angles in any triangle is going to be 180. And sometimes from law of sines, we'll be getting values like 30 or 150, okay? And the issue here is that what is sine of 30 degrees? What is sine of 150 degrees? It turns out that they're both equal to 1/2. Like you were working with law of sines and you got, okay, sine of alpha is equal to 1/2, right? You might use a sine inverse. So alpha would be equal to sine inverse of 1/2, right? And this would give you 30 degrees, okay? But you also could have had an interior angle of 150, right? And the reason why we run into this, and it's just a shortcoming ultimately of the sine inverse function, because these are both possible angles that we could have substituted in for alpha to get 1/2, right? There's 30 degrees. There's 150 degrees, right? Or if we're in terms of radians, this is pi over 6. This is 5 pi over 6. Okay, but the sine inverse function, remember the range of that is just the right half of the unit circle. Like it only outputs values, angle values that are between negative pi over 2 and pi over 2, right? So this could have been the solution over here, 150 degrees, but we wouldn't have found it, just, as an inherent limitation of sine inverse. So what I'm going to propose here is, using this theorem, this property called the law of cosines. Why might cosines be better? Why might this be a better option when compared with sine? Well, thinking about the cosine inverse function, like if we're looking at y equals cosine inverse of x, what is the range of cosine inverse? Right? Rather than looking at the right half of the unit circle, for cosine, we look at the top half of the unit circle. Okay, it's going to return values in this area, which is a great place to be if you're working with right triangles, because these are all the angles between 0 degrees, or 0 radians, and 180 degrees, or pi radians, which is all the possibilities for, the angles of within, an interior angle of a triangle. This is all to say that using formulas involving the cosine function allows us to sidestep pretty much all of the issues that we might run into using law of sines. So I'm not going to do a derivation for this one, but here is the law of cosine. So suppose we have angles A, B, and C, and they're all opposite to side length A, B, and C, just like, in this triangle up here. Okay, same type of triangle that we looked at, same way of defining all the sides and corresponding angles that we did in the previous section. We have the following equations. A squared is equal to B squared plus C squared minus 2BC cosine A. Okay, so that's the first one. I'm just going to draw the triangle here because I feel like if you have the triangle drawn out, it makes this formula seem less daunting. So, okay, let's call this vertex A, this will be B, this will be C, and this will be side length A, B, and C. Again, having, lowercase b opposite to angle B and so on. So A squared, right, that's side length A right there, is equal to B squared plus C squared minus 2BC cosine A. The way that I remember this is I kind of orient myself visually. So like, okay, here's A squared, B squared, C squared, and then cosine of A. Right, so everything is kind of involving the side length A, the opposite angle A, capital A, and then the two sides that are, enclosing this angle A. Okay, so A squared is equal to B squared plus C squared minus 2BC cosine A. Okay, so I'm just describing like visually kind of how I orient myself, like 2BC cosine A, and little a is just that side length on the opposite side. Okay, and then we have the same formula, and the same thing applies to all three sides. So then b squared, okay, so now we're focusing on lowercase b, that's going to be equal to a squared plus c squared minus 2ac cosine b, okay, where b is this angle that's opposite to lowercase b. All right, and then a third one for c squared. Okay, so however you memorize these, I'm totally fine with it, but I tend to look at the picture and, kind of visually orient myself. Okay. One interesting thing about this formula is it turns out that the Pythagorean theorem a squared equals b squared plus c squared, or however you want to look at it, is just a special case of the law of cosines where we have a right angle. Okay, because if we're looking at a right triangle, let me draw one out here. Try my best to make this look right. Okay, so there's our right angle right there. How about I call this angle C, and this will be A, and this will be B. Right, so here's lowercase c, here's lowercase a, here's lowercase b. if I applied the law of cosines to this triangle, and let's say I was looking at, okay, so c squared is equal to a squared plus b squared minus 2ab cosine c. Well, cosine of c we actually know in this case because we're looking specifically at a right triangle. So what is cosine of 90 degrees? Cosine of 90 degrees, or cosine of pi over 2, is equal to 0, right? This is equal to 0. So that means that this whole term on the end is going to drop off. So c squared is just equal to a squared plus b squared. Okay, so just an interesting observation. The Pythagorean theorem is just a special case of the law of cosines where one of the angles is a right angle. Okay, so this is just expanding the Pythagorean identity or the Pythagorean theorem to triangles that aren't necessarily right triangles. So why don't we check out an example, see how this works. So we want to find the remaining parts of the triangle with this angle alpha. This is like our angle A, 65 degrees. We've got a side length B, which is 5, and then a side length C, which is 8. All right, and the way that this all lines up, it's going to be a side angle side situation. So I always start by drawing this. So let's say I'm going to have my angle, or my triangle A. Let's see, how do we orient it up here? Okay. Just to be consistent with the picture on the first page, let's say A, B, C. And okay, so alpha, that's the angle at A. So 65 degrees, okay, that looks something like that, sure. And then the side length B is 5, so that's over here. And then the side length C is 8, so I'll just make sure that's long enough there. Cool, so that's just how I constructed my triangle there. And then I'll fill in, we know this angle at A is 65 degrees. So to find all the remaining parts, really we're looking for side length A, and we're looking for, this angle at B, and then this angle at C. Okay, and then now we can really see that it's a side angle side case because remember, we're kind of looking like consecutively. We've got a side length that's given, and then the angle that's given, and then another side length that's given. Okay, so this is one of those scenarios where law of sines is going to fall short. We're not going to be able to solve this one using law of sines. You can try. I dare you to try. It doesn't work out. So we're going to use law of cosines. And here's how we do this. So what I do is I kind of look to an angle, right? Because law of cosines involves some angle. And we're given the angle A in this case. All right. And then law of cosines also uses the two side lengths that are kind of like on either side of that angle A. Okay, so this is perfectly set up for it. And the other, value that is involved in the formula is this side length, which is opposite to the given angle. So really, what I'm going to do first is I'm going to solve for this side length A. So I'm going to use this first installment of the theorem, okay, because that side length A is what I'm looking for, and it's isolated on one side of the equation. So let me show you how this is going to work out. So I'll just say we can use this formula. A squared is equal to b squared plus c squared minus 2bc cosine A to solve for that side length lowercase a. All right, and the goal is just to use the formula that's going to leave us with just one variable, which we can solve for, and that's what's going to happen here. So, all right, let's do it. So I'll leave a as a variable, but I can plug in for b I have 5, for c I have 8. And then cosine of 65 degrees. All right, so really it's going to come down to just, simplifying the right-hand side there. And this is definitely something that you can do on your calculator. 65 degrees, that's not like a super familiar angle or anything. So you're free to do this on your calculator. Make sure you're in degree mode to avoid any issues. All right, so I just typed this all into my calculator just in one, long expression. And on the right side, I end up with about 55.1905. I just round it to 5 decimal places. And last thing I have to do is I just have to take the square root of that answer. And remember, using that little answer button on your calculator is nice to avoid rounding errors. And here's what I get. I get that a is equal to 7.43. I'm just rounding to 2 decimal places. Okay. And yeah, technically there could be like a plus or minus out in front here, but a is a side length. Okay, so it doesn't make sense to have a negative side length here. So there it is. That is the first thing that I want to solve for here. So I'll just draw that into my picture. So side length A is about 7.43. All right, so now that we are here, we are actually in a position where we can start using law of sines if we wanted to. Okay, because now that I have the angle A and the side length A, and I've got some other side lengths, I have everything I need to apply law of sines. So I can totally do that. But hey, you know what? Maybe just for fun, let's apply law of cosines to find one of these other angles. So how about we start with angle B? So let's try to find angle B here. And what I have is, so first of all, if I'm trying to solve for angle B, that means that I would be using this second formula right here. So I'm going to need to use, all of those side lengths A, B, and C, which I luckily have now. So, there's A, there's side length C, there's side length B. So let me show you how I can solve for the angle B. So now I'm going to use that formula. B squared is equal to A squared plus C squared minus 2AC times cosine of capital B. And then plugging in all my values. So 5 squared is equal to 7.43 squared plus, let's see, C was 8. 8 squared minus 2 times 7.43 times 8 times cosine B. All right, good. So now what I can do is I can solve for the cosine part, all right? So doing that, I'm not really going to multiply anything out just yet. I would do 5 squared, I would subtract 7.43 squared, I would subtract 8 squared, and then I would divide both sides by negative 2 times 7.43 times 8. And all I would be left with on this side is cosine of B. Okay, you can do that in more steps than I just did there, but that's what we would end up with. So here's what I'm going to do. I'm going to type that whole thing that I got on the left side of the equation into my calculator, being real careful about, because when you type this in your calculator, you want to group the whole numerator together and then division sign and then group the whole denominator together, just to make sure that your calculator doesn't get mixed up. So I'll type this into my calculator. And I get this number, 0.79243691112. I just wrote the whole thing out there. All right. And then I'm just going to, take cosine inverse of both sides of this equation. So I'm going to keep working up here because I'm running out of room. So then I get, cosine inverse of that whole number. And, on my calculator, I'm just going to type in cosine inverse of answer, whatever the last result was. And I do this to avoid rounding errors. And here's what I got. I got 37.5, and I'm just going to round to 2 decimal places, 37.59 degrees. And that is the angle B. Okay, so there's that second thing that I needed. So now I can write that in. So that angle B there, whoops, that angle B is about 37.59 degrees. Cool, so, again, that last part, solving for that angle B, I could have done that using law of sines as well. Might have even been easier to do it that way, but I just wanted to show that there's quite a bit we can do with law of cosines. And now all that I have to find now is that angle C, but I'm not going to mess around with law of sines or law of cosines because I'm, trying to save time here. For this, I'm just going to note that angle A plus angle B plus angle C should add up to 180 since they're all in a triangle. So that means that angle C is going to be equal to 180 minus 65 minus 37.59. So do that subtraction, and what I am left with is angle C is equal to 77.41 degrees. So I'll throw a box around that. And that's it. We're done. We have all 6 pieces of information, all 3 sides and all 3 angles. And we did that with the help of law of cosines. All right, so that is the side angle side situation. Let's look at another example where we're given all 3 sides. So we want to find the remaining parts, so really the 3 angles of a triangle with side lengths 5, 7, and 10. So just like always, I'll quickly draw this thing out. So we're going to have an angle A, angle B, angle C. And okay, so side length A is going to be over here, side length B is going to be here, side length C is going to be here. So A is actually the shortest side length, and that's only 5 units. And then C is the longest at 10. And then B is a little bit shorter, looks something like that. Okay, so now I'm gonna just kind of redraw a little bit. I like drawing things to scale, or doing my best to draw it to scale, just because, when I get my numbers, when I'm actually solving for the remaining side lengths or angles, it's nice to just kind of see like, oh yeah, that angle B does look like it's around 38 degrees, just a little sanity check. I like doing it that way. Okay, well, just filling in the numbers that I have. So I have that side length is 10, this side length is 7, that side length is 5. Okay, so what I'm going to do is I'm going to use law of cosines to solve for one of these angles, because law of sines wouldn't help me do that. So I guess I'll start with angle A. It doesn't really matter. You can start with whichever one you want. So I am going to use law of cosines, and I want to make sure to use the formula, because we've got 3 of them. I want to use this first one that involves, that angle A. So I want to use a squared is equal to b squared minus c squared. Oh, sorry, b squared plus c squared minus 2bc cosine A. And I'm using this to solve for that angle A. So here's what that looks like. It's going to be 5 squared, which is 25, minus 7 squared, which is, 5 squared minus equals, geez, it's been a long week. Okay, 5 squared is equal to 7 squared, which is 49, plus 10 squared, which is 100, minus 2 times 7 times 10, and that's equal to cosine of A, and that's my variable. So now, kind of proceeding in the same way I did solving for angle B in the last problem, I'm going to solve for cosine of A. So, I'll have 25 minus 49 minus 100 all over negative 2 times 7 times 10. And then I carefully type this into my calculator, being sure to use parentheses to group that numerator together and the denominator. And what I end up with is about 0.8857142857. Okay. And then on my calculator, I'm just going to find the inverse cosine of the answer. Okay, so then A is going to be equal to cosine inverse of, that whole number that I just found right there. And here's what I get. Inverse cosine of the answer is equal to about 27.66 degrees. All right, very good. So I'll put a box around that, and we are on our way here. So now that I have that angle, so that right there is 27.66, now I just have to solve for one other angle, and then I can use, all the angles adding up to 180 to solve for the last one. And remember, we saw that we could use law of cosines, or we could use law of sines to solve for one of those angles. So you know what? I'm going to use law of sines to solve for, how about let's go for angle B next. So now I'm going to use law of sines to find angle B. So to do that, I might look at, sine of A over little a is equal to sine of capital B over little b. And then plugging in actual numbers for that. Here, maybe I'll keep working up here since I'm out of room. So sine of A, which is 27.66, divided by A, which is 5. And this is equal to sine of capital B over little b, which is 7. So I can just multiply both sides of this equation by 7. Okay, so I'll type that left side of the equation into my calculator, and what I get from that is about 0.649923 and a couple other decimals. But I'm not going to round that off. I'm just going to use the answer button on my calculator because I'm going to look at sine inverse of that number. And what I get from that is about 40.54 degrees. That's just rounding off to the nearest hundredth of a degree. So there's my angle B. Okay, and now all I have left is angle C, and I'm just going to do what's easiest, and I know that angle C is equal to 180 minus angle A, 27.66, minus angle B, which is 40.54, and I put this into my calculator. And I get this angle 111.8 degrees. All right, and there it is. I solved for all three of those sides using law of cosines, then law of sines, and then just all of those angles adding up to 180. All right, so that's about all you need to know in terms of how to apply law of cosines. The last couple pages of this chapter are just, so on page 14, we're looking at, okay, under which circumstances do we apply which formulas, right? Because at this point we have quite a few. We've got all our basic trig functions, we've got law of sines, and we've got law of cosines. So when do we use what? Okay, well, first thing we should be looking for whenever we're, engaged with some problem where we're trying to solve a triangle, first of all, we should think, what type of triangle do we have? Is it a right triangle? If so, this opens up opportunities to apply all of our basic trig functions, right? So doing this whole, if we have the opposite and the hypotenuse side length, we could solve for an angle using a sine function, or cosine or tangent could both be applicable in different circumstances. Also, we have the Pythagorean theorem, right? A squared plus b squared equals c squared if we're just trying to solve for a side length using two other side lengths. These are all awesome formulas, and if we have a right triangle, we know that we can use them, okay? So if it's a right triangle, that's great. That's kind of like the easy case, because we could just apply the basic trig functions and life is good. Okay, what if we have an oblique triangle, so a triangle that doesn't have a right angle in it? Well, then we know we're going to have to start using these alternative theorems like, law of sines, law of cosines. Okay, so which of those do we use? Well, if we have two angles and a side, so that would be like the side angle angle case or the angle side angle, then we can use law of sines. Okay, and then if we have two sides and an opposite angle to one of those sides, then we can also use the law of sines. But be careful, because this is the ambiguous case, right? And by ambiguous case, this is, you might remember in section 5.3, there were some cases where we had, no triangles defined. Sometimes we would have multiple triangles defined. Which would result in solving two triangles, so we kind of had to do double the work. We don't particularly like this case, but it happens. It also has a way of happening on exams. And then there's also the just, single triangle a single triangle case, where the information given, those two sides in that angle only define one triangle. Okay, so the side-side angle situation, we can use law of sines, but we have to be careful because we don't know which case we're looking at until we start playing around with it. Okay, so those are the situations where we could use law of sines, but of course, like we just learned, there are limitations to that, like if we have the side-side-side case, right? Law of sines isn't helpful in this case, and this is when we can go into law of cosines. And then also if we had the side angle side case, I really think of the side angle side as like this kind of like sandwich situation where we have like, a side length A and then a side length B and then like the angle C over here. I kind of think of this as like, when we have everything in a corner defined, this is when it's real nice to apply the law of cosines. Okay. So anyway, that's just another case where we can apply law of cosines. And we would use one of these formulas depending on what we are trying to solve for. Okay, so that's kind of the trick. You might find that you'll look at a problem and you'll try to apply the law of sines and you'll realize that you have too many variables in the law of sines, and then you'll know just basically by trial and error that you'll have to use law of cosines. Okay, so you can memorize this stuff on this in this little block right here, but you also might just find that you can try law of sines first, and if you end up with an equation that has more than one variable, then you'll just know, oh, okay, I think I probably should try law of cosines instead. Okay, and then looking down at page 15, this is just a little bit of practice. Based on the information that's given, which method should we use to solve each triangle? Okay, so for triangle A, this one right here, let's have a look. So yeah, we do have angle, side. You could just have it memorized like, oh, I can use law of sines in this case. But when I look at this, what I think is like, okay, I've got angle B and then I've got side length B. And then I've got angle C, but I'm missing side length C. So since I have this pair of opposite angles right there, that's kind of what tells me that law of sines can work, right? Because I could do sine of 44 degrees over 7 is equal to sine of 53 degrees over C. Right, and I know this is going to work, or this is a viable approach, because I'm just left with a single variable. That's always the goal here, is just get a single variable. So for this one, I would say law of sines would be, my first instinct. Okay. So now for triangle B, looking over here now, so the thing that jumps out at me right away is, hey, this is a side angle side situation, right? And this is kind of like, I have a whole corner of this triangle defined. And the nice thing about this situation right here is I know that by using law of cosines, I can really quickly solve for this side length over here, which I guess would be side length D, just given how we labeled these. And I know that D squared would be equal to 11 squared plus 11 squared minus 2 times 11 times 11 times cosine of D, which is, right in 99 degrees. Okay, so this is a problem where I could, get things rolling by solving for that side length there using law of cosines. Okay, or if you want to take the longer route where you're not quite on your game, but you could still figure out eventually that it's law of cosines, is you could try to apply law of sines and you would realize you don't have enough information to use law of sines. So either way, I think eventually you'd realize law of cosines is the way to go. But, when I see that corner there, the side length and then the angle on the side length, I know law of cosines is going to work nicely. Pretty much the same explanation works for this triangle, right? I've got side angle side going on. I've got that whole corner of the triangle defined. I know I could quickly solve for this side length b using law of cosines. Great. So now for triangle D, technically, we do have side, angle, side defined here. So you actually could apply law of cosines here, but hey, it turns out that the law of cosines in this particular case, where angle C is a right angle, is just the Pythagorean theorem. Okay, so for this particular problem, I would use, maybe Pythagorean theorem to solve for that hypotenuse there. Or I could also use a, let's see, I could start by using a tangent function to solve for that angle theta. So anyway, since it's a right triangle, I have the privilege of using these theorems. So I could use the Pythagorean theorem. I could also, work with a tangent function. Say, hey, tangent of theta is equal to opposite over adjacent, and I could solve for that angle theta. Okay. And this last one here, triangle E. Okay, well, I'm looking at this one and I'm noticing that I have angle B defined. I also have side length B defined. So I've got this thing going on where I've got an angle and its opposite side, which is a good thing when it comes to using the law of sines, right? Because I could set up this relation here. Sine of B over side length B is equal to sine of C over side length C. And I would end up with, just a single variable there. So I think law of sines would probably be the easiest approach here. But, it does turn out that you could also use law of cosines. Because law of cosines, I could use this b squared is equal to a squared plus c squared minus 2ac times cosine of b. Okay, and really I chose to use this version of law of cosines because I have this angle b, so I wanted to, use the version that involves that angle b. And it turns out that, I could plug in 5 for b squared, and then 8 for c, and a is the only thing that I don't have. Okay, so, technically this approach also could work because I'm just left with a single variable a. But, it's your pick here. You could use either approach, and if I'm being honest, this looks like a mess, right? I don't want to have to try and solve for a in this situation. I think it'd be a lot easier. I mean, path of least resistance is what we're after here. So I would much rather just go with law of sines, quickly solve for that angle C, and we've got a much better situation there. So I'm going to go with law of sines. Okay, so you could memorize all that stuff on page 14 if you wanted to. But I think that it's a much more reasonable approach to just kind of try and build your intuition, looking at all these different scenarios and, yeah, just develop your intuition about which approach is going to be the path of least resistance.